Hi guys, this is Dr. Sumian Sabah. Welcome to JIK 224 E-Kuliah series. So this is the third video covering chapter 1, which is structure and stereochemistry of alkenes. So in this video, we will look at the conformation of monosubstituted cyclohexane. So upon completion of this topic, you should be able to draw ring flip of monosubstituted cyclohexane and predict the most stable conformation. So this is the chair-to-chair interconversion of methyl cyclohexane, or it is also called as ring flip. So from one conformation, the chair conformation can interconvert to boat conformation, and finally again to chair conformation. So this is conformation 1 and this is conformation 2. So the most important result in chair-to-chair conversion is that any substituent that is axial in the original conformation will become equatorial in the new conformation. So in this example, in the first conformation, we have the methyl group in axial position. After it undergoes chair interconversion or ring flip, the methyl group will now be in equatorial position. So anything that is initially axial or equatorial, when the ring flip, it will become the opposite. Okay, so if we have axial, it will become equatorial, and if we have equatorial, it will become axial. So to draw a ring flip is that first you have to draw one chair form and add the substituents. So you can pick a ring carbon and classify it as up or down carbon and draw the bonds. Okay, so you must remember each carbon must have an axial and equatorial bonds. So you add the substituent, in this case hydrogen and methyl group, and you can choose any you can place the methyl group in any position, either in axial or in equatorial position. So in this example, we have placed the methyl group in equatorial position. So this is called conformation 1. When the ring flip, okay, the up carbon will become down carbon. Okay, so you must convert up carbon to down carbon and vice versa. So the chosen up carbon now will puckers down. So what happened during ring flip is that this carbon will become down and this carbon will become up. Third step is add the substituent to the second conformation. So you can draw axial and equatorial position. On a down carbon here, the axial bond is down, and ring flipping converts axial bonds to equatorial bonds and vice versa. So the equatorial, in the previous example, the equatorial methyl group will become in axial position. Okay, so when initially the methyl group is in equatorial position, during ring flip, the methyl groups will become in axial position, forming conformation number 2. Okay, let's look at methyl cyclohexane here. When the methyl substituent is in an axial position here, it is gouged to carbon number 3. So you can clearly see this in the Newman projection. You can see that the methyl group at carbon number 1, okay, when you're looking at carbon 1 to carbon 2 and carbon 4 to carbon 5. So you see that there is an interaction or a gouge between carbon number 1 and carbon number 3. You can also see here, when we are looking at this position, this methyl group in axial position, we have a gauge with carbon number 5. So there is an interaction between methyl group here with the carbon at number 5 and carbon number 3. This is if the methyl group in axial position. But if the methyl group is in equatorial position, okay, looking down at the carbon number 1 to 2 and carbon number 4 to 5, you will see that the methyl group is in anti-position with carbon number 3. Okay, you can see here in the Newman projection, the methyl group is further away from carbon number 3. Okay, or we call it anti-interaction. So conformation with substituent at equatorial position is more stable because there is no interaction. Okay, and plus because this methyl group has more room and it is not it does not have interaction with this carbon number 3. So this equatorial position has a lower energy as compared to in axial position. Okay, this interaction between the carbon number 3 and carbon number 5 is called 1,3 diaxial interaction. Okay, the axial substituent interfere with the axial hydrogen on carbon number 3 and carbon number 5. This interference is called 1,3 diaxial interaction. So for example here, this is the methyl group here. There is an interaction between carbon number 3 and carbon number 5. So this is called 1,3 diaxial interaction. So it is least stable. So when the ring flip, the axial methyl will become as equatorial methyl. Okay, so now the substituents are less crowded in the equatorial position. So and it has more rooms as compared to this conformation. So equatorial. This is why equatorial position is much more stable than in axial position. Let's look at another example, which is the third butyl cyclohexane. So third butyl we have here is a very bulky group. So groups like third butyl are so bulky that it will force the chair conformation to the equatorial position regardless of other group present. Okay, because it is so big, it will cause an extremely crowded in axial position. So it will tend to push out the carbon here to equatorial position to avoid the 1,3 diaxial interaction. Okay. Okay, let's look at this example. Draw the most stable conformation of ethyl cyclohexane. So ethyl group has a CH3 and CH2 groups. Okay, so to do this, this is the CH2, CH3 groups, ethyl group. Okay, so the best position is to place the ethyl group in equatorial position. So the most stable conformers have larger substituent at equatorial position. So as a summary, chair conversion or ring flips change the axial and equatorial positioning of groups. The most stable conformation will be the one which has the substituent at the equatorial position. This is the reference, and if you have any question, feel free to email me at my email address. Thank you.